And then James, you can take it away.
Cool. So let me share my screen again.
You're still muted.
I think everyone heard me anyway because you're right next to me, so it doesn't matter. Cool. So let me, as I said, share my screen. Sorry, a little bit of setup involved here. Okay, so yeah, as Grace said, I'm talking about positive Hermitian curvature flow on almost abelian and nilpotent complex Lie groups, whatever the heck that means. Yeah, I'm just going to start with a little bit of motivation for this and explaining what the title means. So I don't really mind if I get through this whole talk or not. So please just ask me any questions along the way. Actually, I'll put my I'll put the slides in the chat. So that should be uploading now. So yeah, please feel free to stop me and ask questions, and we can have a chat about it. All right, so let's get going. So positive Hermitian curvature flow, what is that, right? So we're going to start with the most famous flow, the Ricci flow, which I'm sure everyone's heard of, but let's talk about it a little bit. So say we have a Riemannian manifold, right? So we got a smooth manifold with a Riemannian metric on it. And then the Ricci flow is this PDE, right? So we evolve the metric over time in the direction of its Ricci tensor or minus its Ricci tensor. So locally, this looks like a heat equation. If we do it in the right coordinates, this looks like a heat equation. And so the idea, I guess, is to kind of disperse curvature over a Riemannian manifold or over a smooth manifold to kind of smooth it out and see if we can say something about maybe the topology. So there's this great picture kindly donated by Ramiro to me of the Ricci flow running on this surface of revolution. So you see these points of very high curvature kind of smoothing out as we run this PDE on it. And then eventually it sort of approaches this spherical shape. So the idea is maybe we can use this to say something about the topology of our underlying space, right? So as I said, very widely studied, and there's been a number of very, very nice results proved with this. So let's have a look. So Hamilton first introduced this PDE and solved the first dot point here, which is that if I have a compact three-dimensional Riemannian manifold and it's got positive Ricci curvature, then it has to be a spherical space form. So it's a quotient of the three sphere. So the idea was to evolve this metric here under the PDE and eventually show that it approaches a metric of constant curvature. Okay, so as long as it's got positive curvature to start with, the limiting metric will be constant curvature. So I'm skipping steps here. You have to show existence and uniqueness, and then long time existence, and then limiting things, right? So it's quite a lot of work, but when you show it has constant curvature, you eventually get that it's the quotient of the three sphere, which is very nice. He also did the same in 4 dimensions. So if a 4-dimensional smooth manifold compact has positive curvature operator, then again, you get the same thing. It's a spherical space form, and it's the same idea of the proof. So that was due to Hamilton, and then he wanted to try and use it to show Thurston's geometrization conjecture. Okay, so that was a long effort by Hamilton and many others. Eventually, Perelman solved it. If you don't know the geometrization conjecture, this contains, as a corollary, the Poincare conjecture. So if you have a simply connected 3-manifold without any boundary and it's compact, then it has to be homeomorphic to the 3-sphere, which is one of the very long-standing conjectures of geometry, and it was solved using the Ricci flow. So Perelman famously declined the Fields medal for this one. So very big result using this. Later on, Böhm and Wilking generalized Hamilton's result with positive curvature operator to the n-dimensional case, as you can see here. So if you have an n-dimensional manifold and it has 2 positive curvature operator, which is a slightly weaker version of positive curvature operator, then again, it's the quotient of a sphere. And Brendel and Schoen also used it to prove the differential sphere theorem, right? So if you have curvature, sectional curvature bounded between 1 and 4, then again, you're a spherical space form. So very strong uniformization results coming from the Ricci Flow. So hopefully you're convinced by this point that that's a very successful tool. It's also very interesting to study in its own right. But the question is, maybe we can answer some bigger questions in like other areas in geometry, right? So for example, could we use it to study complex geometry? Okay, could we use this to answer questions in complex geometry? So I'm going to spend a little bit of time talking about why or why not this might be the case. Let's talk a little bit about complex geometry first. So when I say complex geometry, I mean Hermitian and Kahler geometry. So let's talk about that. So if we have a complex manifold, right? So what does that mean? We have a smooth manifold, and we have this J, which is an endomorphism that varies throughout. So essentially, J is this collection of maps going from the tangent space to itself. It smoothly varies over the whole manifold. It squares to minus the identity, and it satisfies this analytic condition here. Okay, so this is called a complex structure, right? The equivalent way to think about this is that M admits a holomorphic atlas of charts. So locally, M looks like C to the N, and when we change coordinates, it's holomorphic. Okay, and this is a theorem due to Nylander and Nuremberg. But it often helps geometrically to think of it as this endomorphism. So for example, instead of thinking as C as just the complex numbers, you could think of it as R2 and J being this matrix. Okay, this squares to minus the identity, and then this gives you a complex structure on R2. Okay, so we kind of generalize that to all manifolds here. So for example, of these things, you got Cn, the complex projective space, Riemann surfaces, smooth algebraic varieties over C. You've got complex Lie groups, many examples of these objects. So we want to do some geometry on this. I haven't introduced a metric on it yet, but we can. So say we have a Riemannian metric on this smooth manifold. Then we say it's Hermitian if it respects this complex structure like this. Okay, so basically what that's saying is if I rotate 90 degrees by multiplying by I, then that shouldn't change angles or distances, right? So that's a very natural condition to have. So we want metrics on our space to respect the complex structure, and that's why we have this condition here. All right. So from here, because J squares to minus the identity, and we have this Hermitian property, we can actually define a two form, okay, like this. So it's a good exercise to show this is skew symmetric, right? So that omega xy is minus omega yx, and it just comes from the symmetry of G and the fact that it's Hermitian. Okay, so worth trying on your own if you're not convinced. Now this is a two form, right? So we can ask if it's closed or exact or something. So G is called Kahler if it's closed, right? So if we do the differential, if we do differential of omega, we get 0. In fact, this is equivalent to J being parallel under the Levi-Civita connection. Okay, so the covariant derivative of J is 0, is equivalent to a manifold being Kahler. So these are, in some sense, the nicest possible metrics you can have on a complex manifold, these Kahler metrics. So the condition is that it's Hermitian and that this two form we get from it is closed, equivalently if this covariant derivative is 0. So what do we get when we have a Kahler manifold and we want to look at, say, the Ricci flow? Well, because of this condition, when you look at the Ricci curvature, it is also Hermitian in this sense, right? It does the same thing as our Hermitian metric. So that means that Kahler metrics are actually preserved by the Ricci flow, all right? And you get a curve of Kahler metrics. And this yields what's called the Kahler-Ricci flow. And this is very well studied, very beautiful theory behind all this. For example, you can use it to prove the uniformization theorem in complex dimension 1, if you like. It's also been used to prove a lot of other theorems in complex geometry as well. So Kahler-Ricci flow, very beautiful. The problem is that not every manifold has a Kahler metric, right? So Kahler metrics are topologically obstructed. So for example, we get from Hodge theory that if we have a Kahler manifold, right, so it emits a Kahler metric, then all the odd Betti numbers are even, right? I know that sounds a little bit weird, but every odd Betti number is an even integer, okay? So this immediately gives us some problems when we try to construct a Kahler metric. So for example, a non-Kahler manifold is the Hopf surface, right? So if we fix some real number, alpha bigger than 0, then we have an action of the integers on C2 without 0, okay? And what is this action? Well, we just act on V with alpha to the n times V, okay? So we just kind of scale it. And then if we take the quotient under this action, so this action is like free and properly discontinuous, so we get a smooth manifold when we take the quotient, it's actually diffeomorphic to S1 cross S3, okay? It's a good exercise to show this diffeomorphism as well. So the idea is S3 sits inside C2, okay? And then you're kind of quotienting out by this lattice so that the other kind of C gets collapsed to an S1, okay? But you can set up a proper map quite easily if you just sit down and think about it for a little bit. So it's diffeomorphic to S1 cross S3, but that means we can compute the Betti number, the first Betti number, for example, right? Betti numbers of products of manifolds aren't too hard to figure out, and we know the ones of spheres. So the first Betti number, this topological invariant, is 1, right? And so it's not even, and so therefore this can't admit a Kahler metric. So on the other hand, any complex manifold will admit a Hermitian metric, okay? So how do we construct one? Well, you just let G be any Riemannian metric on M, and then you just define this new metric being Gx, y plus Gjx, jy, and it's pretty easy to verify this. Okay, so any complex manifold admits a Hermitian metric, but not every complex manifold admits a Kahler metric, okay? So that's a problem, because when a Riemannian metric is Hermitian but not Kahler, we no longer have this being satisfied, okay? So if we try to evolve our metric like this, you can see that this Hermitian condition is going to be broken pretty quickly, right? We want this to be preserved along the flow, but as soon as we evolve it by a tensor that's not going to do that, it's going to break, okay? So when a metric is not Kahler, the Ricci flow is pretty much useless to us if we want to study Hermitian geometry. Maybe I'll stop here and ask if there are any questions. No, people seem to be.
Quick question, I suppose. In the second line of your talk, I suppose you want to use the S1 cross M3 precisely because it admits a Hermitian metric, but not a Kahler metric, right?
Yes.
Okay, cool.
Yeah. So as I said in the line after that, any Riemannian, just choose a Riemannian metric on the underlying smooth manifold, and you can construct a Hermitian metric straight away. And it's pretty well known that any manifold will admit a Riemannian metric. Yeah, maybe you need paracompactness or some crazy second countable thing, but they're very mild topological assumptions. Whereas Kahler geometry is much more obstructed. Okay, cool. Thanks for that. Any other questions? All right, I will move on. So we need to construct a flow that will preserve Hermitianness, right? So we need to kind of look beyond Riemannian geometry a little bit and think about what else we can do. So in that sense, I'm going to define the Chern connection, right? So the Chern connection is the unique connection nabla satisfying the following, right? So we want G to be parallel and J to be parallel. So remember, when we had the Levi-Civita connection, well, let's recall what the Levi-Civita connection is. This one satisfies G being parallel and that the torsion is 0, okay? So the torsion I define like this, okay? So we sort of commute our connection and we add in another term to make it tensorial, but that's the defining characteristic of the Levi-Civita connection. Here, instead of demanding that the torsion vanishes, I'm just asking that J is also parallel. So it's pretty natural that we want a connection to also respect the complex structure. But now, of course, we don't have the freedom to make the torsion 0. So we just ask that the torsion satisfies this condition, that it behaves well enough with respect to J. Okay. And again, the torsion is sort of this commutation of the connection. So one thing we can observe here, that is, if G is Kahler, then that happens if and only if the torsion actually vanishes. So if the torsion vanishes, then G is Kahler, and the Levi-Civita connection is just our Chern connection, our nabla. Okay. So instead of thinking in terms of the Levi-Civita connection, I'm now just going to think in terms of the Chern connection at the expense of picking up torsion terms when I want to do computations and stuff. So for example, we lose the Bianchi identity and stuff from here out, but things aren't too bad analytically. Is that a question? Okay. So from here we can define the Chern curvature just like we would the Riemannian curvature. Okay, so we kind of go to second order here. So we look at so if I expand this term out, this is just this bit here. Okay, and we define it exactly as you would in Riemannian geometry. Okay, but again, as I said, we lose symmetries, right? We lose the Bianchi identity, for example, and things like that because we've picked up this torsion term. Okay, but that's okay. So we just define it in the same way. And then how do you get the Ricci tensor from the Riemannian tensor? Well, you take a trace. Okay, so we call this the second Chern Ricci tensor of the Chern connection, and it's just the trace over the first two entries. So we essentially pick an orthonormal basis, and we sum up over those two entries, and we get this 2 tensor now, right? This is symmetric, and we define it. Yeah, it's just defined the exact same way as the Ricci tensor. The reason I'm saying second here is because, again, since we've lost the Bianchi identity, if I trace over another 2 things, another 2 entries, then it won't be the same. So in general, we get 4 different traces on this thing, and they're all different. Okay. For now, we're going to choose what we call the second one. So now S, which replaces our Ricci tensor, is symmetric, and it satisfies this Hermitian condition now. Okay, so that means when we evolve in the direction of that, it's not going to break Hermitian geometry. Okay, which is what we set out to do. Okay, so in that sense, we can define what's called a Hermitian curvature flow. And Streets and Tian did this in, I think, 2008. And we evolve the metric now in the direction of S instead of Ricci. And we actually add on an extra term, Q of T, which is just some quadratic tensor in the torsion, okay? And it's arbitrary. And so what this gives us is actually a whole family of different flows that we can study, okay? And we can choose Q depending on what we want to do, all right? So analytically, this flow is actually very nice. So this theorem from Streets and Tian says that the flow is strictly parabolic. Okay, so what does that mean? Well, it means that the operator that sends G to S of G is elliptic. Okay, meaning that I can write sort of S of G of, like, say, IJ is like A RS kind of something like this, dx dxs, right, where I sum over R and S, G IJ. Okay, and then this matrix, perhaps I should say, this matrix formed by the ARS is strictly positive definite. Okay. Now, analytically, that gives us very nice things because it follows that there exists a unique short-time solution on compact manifolds, right? Immediately from standard parabolic theory, which was not the case for the Ricci flow. You had to do a lot more work there to actually prove existence and uniqueness. But here we immediately get it. The other thing is when G0 is Kahler, well, what happens? Well, in that case, I said our Levi-Civita connection agrees with the Chern connection. And so S will become the Ricci term. And because torsion is vanishing, this term goes away. And so we just recover the Ricci flow, okay, or the Kahler-Ricci flow. So when our initial metric is Kahler, we do get a Kahler-Ricci flow, and this is a proper generalization of the Kahler-Ricci flow to non-Kahler manifolds. All right. So Streets and Tian in the same paper also proved some nice regularity theorems, and stability results near Kahler-Einstein metrics. Okay, so if you're close to a Kahler-Einstein metric, you'll converge to it, at least under these topological assumptions. If you know what that means, great. If you don't worry about it too much. So yeah, so analytically, this flow is very nice. But again, we've left Q arbitrary, so this result is very general. And the exact choice of Q will depend on what you want to do with it, right? So it depends on your application. So there's a couple being actively studied. For example, what I'm going to call the gradient HCF is one where Q is chosen so that the HCF is the gradient flow of some nice functional. Okay. There's also the pluriclosed flow, where Q is chosen so that this condition, dd bar omega equals 0, is preserved. Okay, so remember the Kahler condition is this. The pluriclosed condition is slightly weaker, meaning every Kahler metric is pluriclosed. It's this second order condition. Okay, and you can choose Q in such a way that that's preserved, and we call that the pluriclosed flow. It's been very well studied. And then the positive HCF, which I'm going to talk about today, is one where we choose Q so that it preserves curvature positivity conditions on Hermitian manifolds. Okay, so if some kind of curvature is positive to begin with, then it remains positive as we evolve the flow. So what kind of questions do we want to answer with this? So far, I've just defined a flow. Perhaps you're not too interested in curvature flows and you wonder what the heck it's useful for. So for example, we might want to use it to prove the existence of a complex structure, or disprove the existence of a complex structure on S6. So there's a natural question, right? If I have a sphere of even dimension, does it have an integrable complex structure, right? Is it actually a complex manifold? So the answer is no. For all n not equal to 2 and 6. Okay. Sorry. For all n not equal to, I guess, 1 or 3. Erase my stuff. But so S2 does admit a complex structure. S4 doesn't. S8 doesn't, and so on. S6, the answer is unknown. So we don't know if S6 is a three-dimensional complex manifold. This has been an open question for a while. We could potentially use a flow to solve this question. So how could we do that? Well, assume that S6 did have a complex structure, right? And take G Hermitian with respect to J. Okay, so run the HCF beginning at G, and then show that GT converges to some G infinity maybe, and perhaps this metric is Kahler. Now this would give a contradiction because it's actually known that S6 does not admit any Kahler metric. Okay, so if you could prove that the flow converges to some metric that's going to contradict the existence of a complex structure, then you're done. Okay, so that's a very ambitious way of proving that very open problem with a flow like this. Okay, and you can see that the motivations for these flows aren't completely vacuous, right? The other one is classification of complex surfaces. So this is a very interesting subset of four-manifold geometry, four-manifold topology. So, for example, all complex surfaces emit pluriclosed metrics, so the pluriclosed flow could be very useful. And indeed, there has been a lot of work in that direction. The other question is uniformization problems with curvature positivity conditions, which I'm going to get into now. So again, we're studying the positive HCF. So it's defined like this, whatever, that doesn't really matter. An example of it working is if the curvature, an example of curvature positivity being preserved is this. So we say a metric is Griffith's non-negative. If this is true for all x and y in the tangent space, then this is preserved under the HCF plus. Okay, and then there's a nice theorem. If it's Griffith's non-negative everywhere and positive at least some point, then we have to be biholomorphic to CPN, which is very nice. Very nice, strong theorem coming from this flow, right? So this looks to be a pretty interesting flow to look at. So I'm going to quickly talk about my work, which looks at this flow with symmetries. Okay, so we want to study what happens when we introduce symmetries into the metric and see if we can gain some more understanding. So recall what a complex Lie group is. It's a complex manifold with a compatible group structure. So these are some examples. Important classes to keep in mind for this talk are the solvable ones. So you should just think of subgroups of upper triangular matrices, and the nilpotent ones, which are subgroups of upper triangular matrices where we demand that there are ones on the diagonal. So for example, this group here, this Heisenberg group, is a nilpotent one. And then we put some geometry with symmetry on it. So a Hermitian metric is left invariant if this is true, right? So if we translate, if we use the left translate function, then it preserves the metric, right? So remember, this function is just one that sends y to x times y. All right, so that's some geometry with symmetry on this group. And in fact, left invariant metrics on G correspond directly to inner products on the Lie algebra, i.e. the tangent space at the identity. Okay, and that means for us that if we flow left invariant metrics on the group, then it's equivalent to looking at an ODE of inner products on the Lie algebra. Okay, so the symmetries simplify analysis slightly. It means we can get some quite strong results. So in fact, Ustinovskiy studied his own flow on complex homogeneous manifolds, meaning quotients of complex Lie groups, equipped with submersion metrics. So I won't get into the details of what a submersion metric is, but if you know, that's good. The important thing is, if I have a left invariant solution on G, then the corresponding submersion metrics solve the HCF plus on G mod H. And this is very special to the positive Hermitian curvature flow, which is a very nice property. And it's independent of the isotropy group. So he studied some results relating the growth behavior to the structure of G. And in particular, the flow exists for all time if and only if G is solvable. Okay, so in this case, there's a very natural question, right? So the flow exists for all time. If G is solvable, what's the limit, right? If we take the limit to infinity, what do we get? So suppose we have a simply connected complex Lie group, left invariant Hermitian metric G. Let's say we have a left invariant solution to the HCF plus. The natural question is, when T max equals infinity, what is the limiting behavior as T goes to infinity? Maybe we want to rescale it. So this is the first result I showed last year. So when G is nilpotent, so not quite solvable, right? So nilpotent is a strict subclass of solvable. But when it is nilpotent, if we rescale the metrics, then these subconverge in the Cheeger-Gromov sense. If you don't understand what that means, don't worry about it. These subconverge as T goes to infinity to an HCF plus soliton. Now, what is a soliton? It's a solution that evolves only by scaling and isometries. Okay, so remember, when we do geometry, we only care about results up to isometry and perhaps up to scaling, right? So for example, a soliton could be like a sphere where it just sort of shrinks to a point. And this is essentially a fixed point of our flow, right? The geometry is really not changing, you know? Another example, which is probably going to come up in the next talk, could be like some shape that just kind of moves along, that moves straight by left translation. It's evolving by isometry, and geometrically it's not changing. So essentially what I showed was that this subconverges to a fixed point, okay? Which is the best you can essentially hope for in this setting. And we do have to rescale our metrics when we do this. And I should mention that the result was shown by Puya when the nilpotent Lie group is in fact two-step nilpotent. So how am I going for time? How much time do I have left? All good?
Maybe about 10 minutes, up to.
10 minutes, cool. So maybe I'll just briefly talk about one aspect of the proof. Okay, and this is the aspect I find most interesting. It's called the bracket flow. Okay, and so this is how we study these kind of problems on Lie groups, right? And this works for pretty much any geometric flow. So it was introduced by Lauret, and then later Bohm and Lafuente improved it for the Ricci flow as well. So suppose we do have a complex Lie group with a left-invariant Hermitian metric. Simply connected is quite important here, but you can always go to the universal cover when you don't have simply connectedness. So suppose we have this. Now I want to study the HCF plus of left-invariant metrics by looking at an ODE of inner products on the Lie algebra. Okay, so how do we do that? Well, for each T, what I can do is look at things in a different perspective. I choose a time-dependent orthonormal basis. Okay, so I have this orthonormal basis for our vector space, meaning this, right? So this depends on time because my metric is moving. Okay, now I can choose this like this is not unique, right? I can choose many orthonormal bases for one metric, but I can choose it such that when my structure constants, okay, so these things, so remember this is the Lie bracket of my Lie algebra, okay, and this gives me Cij k, and this is also going to depend on time, and I can choose it in such a way such that they satisfy this ODE, right, where P is given by this. Now this seems a lot more complicated than what I was just looking at, right? So the key thing is that this is equivalent because I've just chosen a basis, right? I haven't changed anything. I've just chosen a basis and I'm looking at a different ODE. This is equivalent to the original HCF plus. And what is the advantage of this? Well, scale static solutions to this, meaning these guys, right? Ones that evolve only by scaling, they give us solitons. So normally we're looking for a solution that evolves up to isometry and scaling. That's very hard to sort of detect in the metric setting, right? But in the bracket setting, this is much easier to detect. Okay, and this is the advantage of the bracket flow, and this is why we use it. We just need to show convergence of this thing to a scale static solution, and then we get convergence of the original flow to a soliton. So hopefully that convinces you why this trick is kind of neat.
Hi, James. Sorry, just a quick question.
Yeah.
How far is that bottom statement from being like an if and only if kind of condition?
Good question. Depending on what your flow is, either it's if and only if or not. So in the Ricci flow, you do get if and only if. But for other flows, I guess it's unknown usually.
Okay.
So for this flow, it's not true. For the nilpotent setting, it is true, but for the general setting, I guess it's not true. Yeah, good question. But for the Ricci flow, I guess if you only care about the Ricci flow, it is. But hopefully you don't only care about the Ricci flow after this talk. Anyway, thanks for that. So my next result was answering, so I answered it for nilpotent Lie groups, right? But of course the T max equals infinity holds for all solvable Lie groups. So I guess you want to ask about it in that case. Unfortunately, it's quite hard, but you can answer it for a special class, okay? So a complex Lie group, right, which we denote by G sub A, is called almost abelian if there exists some A such that I can write G as the span of these basis vectors, G being the Lie algebra, right? This is the tangent space of the identity. And E0 EI is AEI, and EI EJ equals 0 for all other I and J. Okay, so this has a whole, so this this is abelian. Okay, so this is an abelian ideal, and then this acts as AEI, right, on it with the Lie bracket. Okay, so most of my Lie group is abelian. That's why we call it almost abelian. If you like, you can think of this as meaning there's a codimension 1 normal abelian subgroup. Okay, so if you like an example, just think of the Heisenberg group that I mentioned before. Okay, so in this case as well, when G is almost abelian and non-nilpotent, then even without rescaling, you can get convergence as T goes to infinity to a soliton as well. Okay, and in this case, it's really nice because your whole Lie bracket that I was talking about, so this bracket flow, your whole Lie bracket is in a matrix, and so the bracket flow is equivalent to this flow of matrices. Okay, and this is very nice. So A star is the what is it, the conjugate transpose, and this commutator is just equal to A star minus A star. So very down to earth ODE, nothing crazy going on, just a flow of matrices. So how do we do it? Well, we define this Frobenius norm as just being the trace of A star. And then you can evaluate the derivative of it just by plugging in what this means, well, what this is to it. And then you can show that the derivative of this norm is actually less than or equal to 0 by the Cauchy-Schwarz inequality, okay? So immediately you see the norm is decreasing, so this has to live for all time. The only way this would only exist for finite time if A blew up, but it can't blow up because the norm is bounded. And when does equality happen? Equality happens if and only if our matrix is normal, okay? Which immediately implies that A dot equals 0, which is clearly a scalar multiple of A. So what we get a quantity that's decreasing for all time, and it's stationary if and only if my bracket flow is scale static. And that means that the flow has to converge to a soliton, all right? And that completes the proof in that case. So very robust when you have an almost abelian Lie group. Okay. Any questions so far? No? Okay. So just one more thing on almost abelian Lie groups, and then I might wrap up. So we can also classify solitons in this case. So we show that the flow converges to solitons, but we don't really know what they look like generally. In fact, on almost abelian Lie groups, we do know. So if we have, say, simply connected almost abelian, and it's parameterized by some matrix G sub A, then this admits a left-invariant soliton if and only if A is semi-simple, meaning it's diagonalizable, or it's nilpotent. Okay, so what does that mean? So either A up to change of basis looks like that, or up to change of basis, it is upper triangular, right? But if it's any mix, if it's not strictly upper triangular or strictly diagonal, then that Lie group doesn't admit a soliton, right? And you can also show uniqueness up to isometry and scaling by constant, all right? Yeah. So one little thing I want to say to maybe advertise this a little bit is that the proof is constructive. And so you can actually yield explicit examples of solitons in all dimensions, okay? And all nilpotent examples admit compact quotients. So if you only care about compact manifolds, then in fact you can find a soliton, sort of a non-compact Lie group admitting a soliton metric, such that if you take a quotient by a lattice, you get a compact manifold, okay? So classifying solitons in almost abelian is pretty much complete at that point. So I think I'm pretty much out of time, so I'll probably leave it there. I'll show you some references now. But if there's any questions, I'd love to hear. Thank you very much.
Thanks, James, for the talk. Are there any questions?
Do you know, in the case of S6, what the obstruction, why we don't know if there is a Hermitian manifold, like metric on it?
That's a good question. I do know for what's the other one that emits it? S2, it's pretty easy, right? Because you just look at the quaternions, I think, and that gives you the complex structure. Maybe. Or maybe I'm wrong.
It's just the Riemann sphere, so you can take it as the standard.
Oh, yeah. Yeah, S2 is easy, right? Yeah. So S2 is the Riemann sphere, so that easily admits a complex structure. Why it's so hard for S6, I couldn't tell you. That's a very deep question.
Lawrence, remind me when next we see each other, because I've got a paper on the same topic for my own thesis. So I've got some interesting history of the problem. It's apparently quite involved. They've had whole conferences on it before, so there's a lot of stuff to dig into.
It's one of those things that gets solved every couple of years, but then they find a mistake.
Something wacky must be going on then. Thanks.
Are there any other questions for James?
I have a question. So right at the start, you gave a description of a complex manifold, and you said that it was equivalent to
Yes.
having a biholomorphic atlas. Can you give me an intuition for why these two things are equivalent? Is it complicated?
One direction isn't too hard, I think, if I remember. So I mean, the easy direction, I guess, is this one, right? So if it has a holomorphic atlas, you can construct this J. So what you can do is spanning your tangent space, you have these operators. You have these guys.
Mm-hmm.
Okay, so they span your tangent space. So sort of Zi is x plus I y, and Zj is x minus, well, xj bar is xj minus I yj.
Mm-hmm.
Okay, and then these things are what? This is d by dx I minus I think. And then the other one is a plus, you take the conjugate. Okay, so what you can do is then you can define J to act like this. So you just do that. So this is, you make it multiply these unbarred ones by I, and you make it multiply the conjugated ones by minus I. Okay, and so when you define J like that, you can show that it satisfies this pretty easily, and you can also show that it satisfies this by subbing in these basis vectors into here, and then showing that the J acts appropriately and satisfies that analytic condition. So the other direction is much harder because you have to take this J and then you have to construct this holomorphic atlas, right? You have to construct these coordinates from it. I wouldn't be able to tell you exactly how to do that, but it's a pretty deep theorem going the other way.
Mm-hmm. Okay, interesting. Thank you.
No worries.
Hey, James, I have a question.
Yeah.
So on slide 14, when you're proving your theorem.
Yes.
So you say that right at the end, that in order to, I guess, complete the theorem, you need to show that there are the scale static solutions to your bracket flow. Is it obvious how you prove that there are those solutions? How do you prove that there are scale static solutions to the bracket flow?
Not every manifold will admit these scale static solutions, right? Not everything admits a soliton, as I said in the last theorem, right? If your A is not in the right way, then the manifold won't admit it. So yeah, existence is a harder question, I think. So convergence to it is in the, I guess the question is, how can a manifold not admit one, and then somehow you're converging to it in the flow in general? I guess that's the natural question that you have in mind, right?
Well, so I mean, you prove that it does admit a soliton, right, in your case. So for your assumptions in your theorem, how do you then show that eventually you admit scale static solutions to the bracket flow, like to prove the theorem?
Yeah. So to do this, you have to construct basically a monotone quantity, like I did in the proof of the almost abelian, right? So you construct a monotone quantity so it's always decreasing, and then it's stationary if and only if you're at a scale static solution. Okay, and then it follows that you have convergence, right? After some technical difficulties. Does that make sense? So I didn't talk about it for the nilpotent case, but you essentially have to do it inductively on the degree of nilpotency. I skipped over that because I was running low on time, but this is the key thing, right? You show that convergence to a scale static solution of the bracket flow. How do you do that? You construct a monotone quantity, so it's always decreasing, and stationary if and only if you're at a scale static solution. So as t goes to infinity, since it's always decreasing, it has to end up at a scale static solution.
Okay. Okay, thank you.
No worries.
Great, we might leave it there. So everyone please thank James again. Thanks, James, for the talk. So I'll stop the recording.